Chapter 10, the t-test for two independent samples, Part 4. In this lecture, I'd like to discuss the role of sample variance and sample size in the independent measures t-test. And we'll start with discussing the basic structure of the t-test, which is here, as I've written, t is equal to the mean difference over the standard error. Whether we're engaging in a single sample t-test, which was in Chapter 9, or a t-test for two independent samples, or what we'll learn about in Chapter 11, which is a t-test for repeated measures, the structure of the t-statistic is always the same. The numerator represents the mean difference, and the denominator always represents variability. In particular, standard error is measured. So in Chapter 9, we identified several factors that can influence the outcome of a hypothesis test. For the independent measures t-test, the obvious factor is the size of the difference between the two sample means. So in our t-test for this chapter, we're looking at the sample 1 mean minus sample 2 mean minus the null hypothesis, which is represented by mu1 minus mu2. A large mean difference increases the likelihood of rejecting the null hypothesis and increases measures of effect size. So again, we're saying that if this value is large, so large mean difference leads to a large, I'll just put my arrows, large t-statistic, which then allows us a greater opportunity to reject the null hypothesis. Again, if we're using a two-tailed test, again in the center, the mean difference is represented by the null, and that's equal to 0. And a larger t always means that it's being pushed out into the tails. Again, if there's a large mean difference, we're saying there's differences occurring between these samples that are representative of two different populations, and that's our hope. We're hoping that we do see a difference due to treatment or due to the fact that there's some difference in the conditions of the quasi-independent variable. So again, based on the structure, if the numerator increases and all else is held constant, the t-statistic increases and moves further out into the tails, enabling us greater opportunity to reject the null hypothesis. And as I just indicated, it also increases the measures of effect size. The measures of effect size affirm the conclusion of rejecting the null hypothesis, or vice versa. It may affirm that we failed to reject the null hypothesis if the t-value isn't large enough to fall into the critical region. But essentially what I want to convey is that the mean difference does have an effect on measures of effect. And that would make sense because the measures of effect are looking at the mean difference, and that's what's represented in the numerator of our basic t equation. So now we want to look at the other factors that we discussed in Chapter 9 and also in Chapter 8. The other two factors that play important roles are the variability of the scores, and again that's indicating the spread of scores, and the size of the samples. Both influence the magnitude of the estimated standard error in the denominator of our t-statistic. Specifically, the standard error is directly related to sample variance. Large variance leads to large error and is inversely related to sample size. Large size leads to smaller error. So again, now we're talking about the denominator of this equation, so the standard error. And we know that, again, we have different equations for the standard error, but to make things a little easier, let's just use what we learned in Chapter 8. So the standard error, the actual standard error, is equal to the standard deviation of the population over the square root of n. And we have learned the variations of that equation for Chapter 9 for single sample t-test, which is our sample standard deviation over the square root of n. And in this chapter, the estimated standard error of the mean difference, they all have the basic same structure. We have variability represented in the numerator and sample size in the denominator. And so in this equation, we have our pooled variance over n1 plus our pooled variance over n2. So again, they all have the same structure. As I just mentioned, the numerator here, here, and here are all representative of variability. And the denominator is all representing the size of the sample, whether it's a single sample or multiple samples, as we see in this chapter for a t-test of independent samples. And I've shared with this little notation with you in the past. So as variability increases, standard error increases, and t-statistic decreases. So again, if we're talking about the standard error equations, any three of these, if the variability increases, so the numerator of those equations increases, the standard error increases as well, because again, that's reflective of variability. And therefore, the denominator of our t equation increases, and when you divide by a larger number, the quotient, in this case our t statistic, decreases. So again, as variability increases, standard error also increases. Makes sense because they're both reflective of variation, differences between scores, and our t statistic decreases. If our t value decreases, again, if we're considering a two-tailed test, that means our t is closer to the center, which is 0. And if our t is closer to 0, the likelihood of rejecting the null hypothesis decreases. We have less ability to reject the null because the t isn't being pushed out into the tails or into the critical region. By contrast, larger samples produce smaller standard error and larger t-statistics. So again, given our equations here, all of these equations for computing standard error, whether it's the actual or estimated, as the denominator, the sample size increases. Again, if your denominator increases, this value is going to decrease. So if our standard error decreases, then that means that the standard error here is smaller and has an influence on our t. In particular, it will increase our t statistics. So again, as n increases, standard error decreases and t statistic increases. So again, opposite of what we just saw, the t value is pushed out further into the tails and consequently increases the likelihood of rejecting the null. Again, this influence is all mathematical in terms of the sample size. We know that larger samples are more representative and we want to use large samples, but we need to recognize the mathematical impact on our equation. So in this case, again, we can see with the equation, if you divide by a larger number, the quotient decreases, not only in the standard error equation, but also in our t-statistic equation. The standard error decreases and our t increases. So we see how these two factors, sample variance and sample size, have great implications for our concluding statements in terms of rejecting the null hypothesis. Again, we see that variance, in a sense, obscures the effects of a treatment or obscures the differences between quasi-independent variables. The researcher has no control over variability. Again, the ideal scenario for a researcher is large mean difference, low variability, and we know that variability is influenced by large sample size. So we can influence standard error by increasing our samples, but we have no influence over the variability of the samples that we select. So that's something that's out of our control. but the standard error given these equations can be somewhat influenced by the size of the samples that we opt to use. And along those lines, although variance and sample size both influence the hypothesis test, as I just noted here, only variance has a large influence on measures of effects such as Cohen's d and r squared. Larger variance produces smaller measures of effect size, which should make sense because, as I just indicated, greater variation obscures or makes it more difficult to detect patterns of a treatment effect or differences between quasi-independent variable conditions. Sample size, on the other hand, has no effect on the value of Cohen's d and only a very small influence on r squared. So again, I'll repeat that. Variance does influence measures of effect size, but sample size has none or very little effect on measures of effect size. The following example provides a visual demonstration of how large sample variance can obscure a mean difference between samples and lower the likelihood of rejecting the null in an independent measures study. So I'm going to walk you through example 10.5 using the next slides, and we'll compute the necessary statistics to again see how increased variation or variability obscures or makes it more difficult to detect patterns of the treatment effect or differences between the quasi-independent variable conditions. Figure 10.6 shows the results from a research study comparing two treatments. Notice that the study uses two separate samples, each with a sample of 9 participants per sample. And there is a 5-point mean difference between the two samples. So again, the first sample mean is 8 and the second mean is equal to 13. So that is equal to 5-point mean difference. The frequency distribution in this figure also shows a clear difference between the two distributions. The scores for treatment 2, those in blue, are clearly higher than the scores for treatment 1 in white. So again, we see these distinct normal distributions for each treatment condition, and they don't overlap, and they are distinctly different from each other. And we would expect that the t-statistic for this research would be quite high. So I'm going to walk you through the steps of producing our t-statistic and putting it to the test with our alpha level and determining the critical region, and also calculate our Cohen's d and r squared to see if in fact this visual is lending itself to rejecting the null hypothesis. So to begin, step 1 always indicates that we state our research and our null hypothesis. This example does not give us the context of the particular research or the independent variable that the treatment illustrates. So we're just going to be very generic. Our null states that population 1 will equal population 2, that we will see no mean difference between these two groups. The research or alternative hypothesis states that there will be a difference, and therefore population 1 will not equal population 2. Step 2 says that we need to set our criteria, so we need to figure out what our critical t-value is. And we're going to implement a two-tailed test, so that value is going to be positive and negative. And we're going to apply, let's say, 0.01 to be very stringent in our research, very conservative. And again, this is a two-tailed test. So now we're going to use our t-table to determine what that critical t-value is, but we need one more piece of information, and that is degrees of freedom. So we know that that's n1 minus 1 added to n2 minus 1, and we have our sample sizes denoted here, so degrees of freedom is equal to 9 minus 1 is 8 plus 8, and we have 16. So let's find our critical t given these parameters. So here is our t-distribution. We indicate the alpha was set at 0.01, a two-tailed test, and degrees of freedom was equal to 16, 8 plus 8. So we're just going to see where these values intersect with one another, and we get a critical t equal to 2.921, positive and negative. So again, given our t-distribution, we get a critical T of 2.921. So we set the critical region. Again, two-tailed test. In the center, we have the mean difference from the null, which indicates it would be equal to 0. And we set our critical region. We're hoping that our t-statistic falls in the tail. And the cutoff point is positive 2.921 and negative 2.921. So that sets the criteria for our t-test, and next we're going to compute our t-statistic given the data that was provided. So here I've set up our t equation. Again, t is equal to the sample mean difference minus the population mean difference coming from the null hypothesis divided by the estimated standard error of the mean. I've replaced the variables that we know, so t is now equal to 13 minus 8 minus 0. Again, this is representative of the null hypothesis divided by the estimated standard error of the mean difference. So 13 minus 8 gives us 5 for our numerator, and our denominator is going to require some calculation. So our estimated standard error of the mean is equal to the square root of our pooled variance over n1 plus pooled variance over n2. So now we need to calculate our pooled variance, and to do so we need to take into consideration what variables were provided. So we've become accustomed to calculating pooled variance using our SS, or sum of squared deviations, and in this case we're given standard deviation. So instead of using this equation, which we have readily used, doesn't make sense given what we have. It's possible, but we'd have to do a lot of algebra to then solve for SS. So the alternative equation that we should use is the following. So the other equation that was presented in a previous video and has not been used in lecture videos but is demonstrated in example videos is variance of our first distribution multiplied by degrees of freedom for our first distribution added to the variance of our second distribution plus, oh, excuse me, that's not an addition, it should be multiplied by. So we have degrees of freedom of our second distribution over the summation of degrees of freedom for both distributions. So something to note, we need variance, we need this variable, but we were given standard deviation, so this is a good point at which we again affirm our understanding of how these variables are related to one another. We know that standard deviation is the square root of our variance, so to produce variance we would just square 1.22. So in your calculators, if we square 1.22, you should get 1.4884. And to simplify things, I'm going to round to the 10th place just to make the math a little easier to digest for this particular example. So we'll report our variance for our first sample is 1.5. And since the standard deviation for the second distribution is the same of 1.22, again, to calculate the variance, we just square that. We square 1.22, and again, you'll get 1.4884, and we're just going to round and use 1.5. So now we have what we need to replace variables in this equation. So our variance of our first distribution is equal to 1.5. The degrees of freedom is equal to 8. Added to 1.5 multiplied by 8, and then divided by degrees of freedom, 8 plus 8. So in our calculators, take 1.5 multiplied by 8, add it to the product, or you could just multiply by 2 and divide by 16. And it should be no surprise that we would get 1.5, because what we're doing is averaging the two sample variances, and they're equal to one another. So we're just taking the average of those two. They're equal, so the average would be the same. So our pooled variance is equal to 1.5. So we can enter that in our equation here. So 1.5 over 9 plus 1.5 over 9. And now let's find out what our estimated standard error of the mean is equal to. So in your calculator, enter 1.5 divided by 9 and multiply it by 2, or add it to, again, the second fraction of 1.5 divided by 9 and take the square root. And your calculator should produce something that looks like 0.5773, and we're going to round to 0.58, again, just to simplify the math a bit. So now, given these steps in this alternate equation for pooled variance, we have our estimated standard error of the mean, so we can compute our t-statistic. So then it becomes 5 divided by 0.58, and now we can compute our t-statistic and compare it to our critical region value. So our t from this equation, 5 divided by 0.58 gives us 8.62. Wow, that's a very large t-value. And again, our critical region was set at, given alpha at 0.01, which is very conservative, 2.921 positive and negative 2.921. So we would assess where this t-statistic equal to 8.62 would reside, and we would conclude that it's somewhere way over here. And it gives us very good reason to feel confident about rejecting the null hypothesis. We would reject the idea that these sample means are equal to one another and now have support for this idea that they are different. To summarize, the conclusion affirms that there is a treatment effect, that these two populations represented by the samples that we selected and tested are different. And again, as a result, we get to reject the null hypothesis. Next, let's calculate the measures of effect. And so that when we change the variation of the samples, we can see the implications for effect size. So we'll begin with Cohen's d and also calculate r squared, and then use those values to compare when the variation of the samples is altered, or in particular is increased. So our Cohen's d equation is d is equal to sample mean 1 minus sample mean 2 over the square root of our pooled variance. So let's replace variables. Again, we have 13 minus 8 over the square root of 1.5, which was what we calculated as the pooled variance. So 5 over the square root of 1.5 in your calculator. Enter 5 divided by the square root of 1.5, and we should get 4.08, or if we round, 4.1. And what this value represents is that from this mean value of 8 to 13, that's equivalent in raw score points as 5 points, but now we've converted into a standardized unit of measurement, and that it could be expressed as 4.1 standard deviation units. Now recall that anything above 0.8, close to 1 standard deviation unit, is considered very large. So this is significant. We're showing great differences between these two samples that are representative of two different populations. So the shift is equal to 4 standard deviation units, or you can think of 4 z-scores that have increased from one treatment or treatment 1 in comparison to treatment 2. So again, this is very significant and supports this t-statistic that was calculated, and also bolsters the conclusion to reject the null hypothesis. Our next statistic is r squared, and that's equal to t squared over t squared plus degrees of freedom. Our t-statistic is 8.62. We're going to square that. 8.62 squared added to degrees of freedom for this case is equal to 16. So in our calculators, square 8.62, and that gives us 74.3044 over 74.3044 added to 16, and that gives us 90.3044. And do this calculation. So 74.3044 divided by 90.3044, and we get 0.822, or simply 0.82. And from our table, when we learned about r squared, anything above 0.25 was significant. So we're saying 82% of the difference in scores is due to treatment. Again, 82, we convert that statistic into a percentage and read it as I am going to state here. 82% of the difference that we're seeing in scores, the difference in the white scores compared to the blue scores, is due to the fact that the second sample received some form of treatment. So that difference is explained by the exposure to the treatment that was administered. Again, very significant. Anything above 0.25 is considered a very large effect. So now what I'm going to do next is show you the same research, but the variation of the samples will be significantly increased from 1.22 to a larger number, and we'll see the effects that has on the hypothesis test as well as the measures of effect. Figure 10.7 shows two samples from different treatment populations. The data is almost identical to the previous example, but what has changed is the variability of these two samples. So the previous example illustrated standard deviation of 1.22 for both treatment 1 and treatment 2. So now we're going to demonstrate how the t-statistic will be adversely affected by this increase in variability. Now the visual should give you some sense of how difficult it may be to produce a t-value large enough to reject the null hypothesis. It's hard to see or detect the effects of the treatment because the variation of the white boxes, right, is similar to the variation of the blue boxes. In other words, there's great variation within both samples, and great variation, which is illustrated through variability, measures of variability that include variance and standard deviation, it obscures or makes it more difficult to detect patterns and to detect true differences between these samples that are representative of two different populations. So we're going to walk through the same steps that we did for the last example to conduct a t-test. We'll begin with our research and null hypothesis. So briefly, the null states again that population 1 will equal population 2, that we'll see no differences, and the alternative says the opposite, well, that they will not equal, that we will see a difference. We'll set the criteria, which is step 2, again based on alpha 0.01. We're conducting a two-tailed test. Degrees of freedom, that has not changed, is equal to 16. So our critical T also has not changed. It's plus or minus 2.921, so that helps us set the boundaries of our test, of our hypothesis test. Again, in the center is 0, the anticipated population mean difference denoted by the null, and we've set our critical region on the negative side and positive side, and the critical t-values are equal to negative 2.921 and positive 2.921. And now we're going to calculate. Step 3 indicates collect your data, calculate your t-statistic, and we have the statistics or the variables necessary to do so, so that will be the next step. So here is the structure of our t-test. Again, the numerator represents the mean difference and the denominator represents the standard error. And I've replaced variables where we have 13 minus 8, again a mean difference of 5 points, and we need to calculate our estimated standard error of the mean. Again, it's not going to be equal to the last example because the standard deviation of both samples has significantly increased. So we're going to use our pooled variance equation here where we utilize variance. So to calculate variance, we simply take our standard deviation and square it, and we'll round to simplify the math slightly. So we square 6.65 and we get 44.22, and that would be the same for both samples. So now we can replace variables in our pooled variance equation and state that our pooled variance is equal to 44.22 multiplied by 8 plus 44.22 multiplied by 8 over 16, and that gives us, in our calculators, it should be no surprise, which is equal to 44.22, because it is the average of the pooled variances representing the average of the two variances of the samples that we are testing. So our pooled variance is equal to 44.22. In our text, it does reference 44.25, but that is a typo. The calculation should yield 44.22. Now we can calculate our estimated standard error of the mean difference. So this would equal the square root of 44.22 over 9 added to 44.22 over 9. So we'll take the summation of those two fractions and then take the square root, and that will produce our estimated standard error of the mean. And we should get, and I'll write it down here, I'm sorry I ran out of room. So our estimated standard error of the mean difference, once we complete that calculation, should yield 3.13. Again, we may have slight differences because of the displays on our calculators, but they should be quite similar. So you may be off by a thousand, hundreds, tens, whatever it may be, but it should be somewhat close. But I do want to let you know that given the span of our calculator displays, we may have some differences in our final answers. And so now we can replace in our equation, in our t equation, the variable that represents variability, our standard error statistic, and we just calculated that, and that's equal to 3.13. So notice the difference. In the previous example, if you recall, the estimated standard error was equal to 0.58. Again, dividing by a smaller number increases the t-statistic, the quotient of that equation. Here we're dividing by a larger number because variability has increased significantly. So the standard error reflects that increase, and now our t-value is affected by that, and we're taking the mean difference of 5 and dividing it by a larger number, in this case 3.12. So let's calculate our t-statistic. So in our calculators, 5 divided by 3.13 gives us 1.597, or we could say 1.6. So that's our t-statistic. Given the parameters that we had set for our test, again in the center we have 0. Our critical t was set as negative 2.921 and positive 2.921. And now we're going to assess where this t-statistic resides. Again, the critical region, the blue areas, are the ideal place in which we hope our t-value resides. In this case, we see that it is less than our critical t, and therefore we fail to reject the null because the t-value is not significantly different from 0. Again, that t-value is representative of the mean difference, and we're looking at how far away that mean difference is from the hypothesized null difference, which is equal to 0. In this case, we conclude it's not different enough for us to conclude that there's a treatment effect. So we see the effects here of increased variability. The increased sample variability increased the standard error, which then meant that our t-value was smaller, and as a result did not enable us to reject the null hypothesis. So the next step, I want to demonstrate the calculation for Cohen's d and r squared so that you can see the effects on the measures of effect. And we should anticipate that those are influenced by variability. So here I have the equations for estimated d and r squared. So d is equal to the mean difference divided by the square root of our pooled variance. So I've replaced our variables here. So if you take 13 minus 8, that's 5, divided by the square root of 44.22, we should get a statistic equal to 0.137, or we can round to 0.14. I apologize. I'm looking at my notes incorrectly, and that's the value for r squared. So again, in your calculators, you probably came up with something very different, and that did not make sense. So, excuse me, so in your calculators, 5 divided by the square root of 44.22 should yield a value equal to 0.751, or we could say 0.75. And again, anything above 0.8 is considered high. So this would place it in category of medium effect size. So Cohen Z, it's not significantly low, but it isn't as high as we saw when the variability of the samples that we tested was much lower. So now, since the variability denoted by the standard deviation values has increased significantly, we see the impact it has on this measure of effect, in particular Cohen's D. So it's now decreased to 0.75. So what we're saying is the mean difference is now expressed in standard deviation units. So it's hard to even illustrate this. Again, the mean here, right, of 13 versus here is now equivalent to 0.75 standard deviation units. Standard deviation units, which is minimal. It's a small effect size. So now our R squared, we should expect that there to be an influence as well, given the increased variability of the samples that were tested. So our equation is t squared over t squared added to degrees of freedom, so we replace variables. And here the value, as I had stated earlier, we should get 0.137, or we can just cite 0.14. And we can interpret this as 14% of the change in scores, or the difference in scores, or the variability. All of those things are indicating the same thing. So 14% of the change in scores is due to the treatment. Again, given the table that we were provided, 0.25 is considered very large effect. So this is on the low to medium side. And so again, we would conclude that the effect of the treatment is not significant. And both of these statistics support our conclusion to fail to reject the null. We failed to reject the null because the T did not fall in the critical region, and these statistics support those conclusions. And again, the purpose of this example was to illustrate the impact that higher variability has on the T statistic and on the conclusions that we would draw, as well as the measures of effect. So here we see that the T was affected and the measures of effect size were also impacted because variability was significantly increased. And again, given this visual, it really does obscure the differences or the effects of the treatment. And think about it, if you have great variation to begin with, right, great differences, and then there's a shift, right, in those scores, it's very hard to assess that the shift in scores was due to treatment opposed to the fact that there was great differences to begin with. So when there's great variability, it's hard to detect true treatment effects because we can't really pinpoint did the scores that we see after treatment or those that were exposed to treatment differ because the treatment was effective, or is it just because the scores were very different from one another to begin with? So that concludes this lecture on the effects or influence or role of sample variance and sample size. And these implications apply to all the t-tests that we're learning about. The single sample t-test from Chapter 9, the t-test for two independent samples, and then the Chapter 11 t-test, which is referred to as the repeat measures t-test. So all of the implications of sample size and variance can be seen in all three t-tests. In the next video, I'm going to talk about the assumptions that underline the independent measures T formula and talk about this idea of variability of these samples since we're using two independent samples. And that concludes this video of Chapter 10.